All right. So in previous lectures, we've talked about Newton's first law, how an object could be at rest if all the forces acting on it are zero and canceling out, or an object could be moving with uniform motion in a straight line, and all the forces could still sum to zero. And it's two different types of equilibrium, but the point is that the forces are zero, and an object will continue doing what it's doing as long as that's the case. Secondly, we've talked about Newton's second law, where the forces on an object or a particle are unbalanced. All right, now in that case, where the object's forces are unbalanced, we actually get an acceleration. So we're talking about dynamics of a single particle. So now we're going to dive into Newton's third law, where we have two things that are interacting with each other, like two objects. So with Newton's third law, instead of describing the dynamics of a single particle, we're going to use this to describe the interaction of two or more particles. And Newton's second law doesn't do this. With Newton's second law, it's the dynamics of a single particle, and it does not describe interactions between two or more particles. So essentially what we're going to do is we're going to discuss interactions, which is just the mutual influence of two objects on each other, okay? So now we're talking about what two things are doing to one another. For example, if you sit in a chair, you apply downward force, but then of course the chair applies a force upward. So those two things, if you're not moving, cancel each other out, but that's an action-reaction pair or an interaction between two objects. Okay, so if object A exerts a force on B, okay, so we have A on B, then Newton's third law says that, well, if we have an A on B, then we should have an A on, or a B on A force, okay? So if A acts on B, then B will exert a force back on A. So now we have a B on A. So this is an action-reaction pair. Okay, we have some object doing an action, so A on B. Then we also have the reaction, B on A. And these, of course, only exist in pairs. So let's look at an example here. So we have the obvious hammer hitting a nail. Obviously, the nail is going to feel a force because it moves. We can draw that. So obviously we have the force of the hammer on the nail, but what you may not think about is we also have the force of the nail on the hammer pushing back. So this is, you can feel this in your hand. If you hit really hard, you know, you can maybe feel like that bruising in your hand or something. So the whole idea here is essentially equal opposite reactions. Usually the reaction force is not as intuitive. You don't think about it as much, just like the action on the hammer here, but it is there. Same thing here with the action-reaction pair forces. So perhaps we're pushing block A into block B. Well, we have that force of A on B, but then Newton's third law says that block B must push back with equal and opposite force on block A. So this is actually, we've been using this idea a little bit because this is where our idea of a normal force comes from. Because when we push on a wall or our weight's on the floor, we're getting that force back. That's an action-reaction pair. All right, so let's apply this to a quick thought experiment. Given Newton's third law, does this mean that a ball, if we were to drop it and it's in free fall, okay? So this ball falling in free fall, if it's under the influence of Earth's gravity, does that mean the ball is also pulling up on the Earth while the Earth pulls it down? So in other words, since there's a force of the Earth on the ball, is there also a force of the ball on the Earth? And the answer is yes. Newton actually realized this from looking at the Earth's tides, okay? So Newton knew that Earth's gravity holds the moon in place as it goes around the Earth in its orbit. So he knows there's an object A that's doing something to object B. Okay, there's our A-B action. But then he realized there was also a reaction. Okay, so we have the moon's gravity. Okay, we have the moon's gravity causing tidal bulges on the Earth, which means the moon is actually pulling back on Earth. So there's our reaction B on A. Okay, and this equal opposite reaction idea had evidence, and people realized that, you know, back in the day, even Newton sort of put this together. So yeah, it does make sense that a ball being dropped would actually pull back on the Earth. But obviously the Earth is so massive, it's not going to like move and accelerate. You also have to think about how much these things weigh. So when we decide what objects we want to look at and what we want to think about as far as interaction, we pick those out, but we're starting to realize there's a lot of stuff going on in these problems, just like the hammer and the nail. So we're only interested in the hammer and the nail, but the nail is also interacting with like the wall that is being hammered into. Earth's gravity is still acting on the hammer and the nail and the wall. So there's so many extra forces in there, it's starting to get cluttered. So let's talk about looking at this like a system and environment approach, okay? So a system is essentially just the set of objects that we want to analyze, okay? So the system sort of ignores everything else as far as what's included, and only narrows it down to just the two objects we're looking at. Okay, now if we talk about the environment, that's everything else not in the system. So that'd be like the wall acting on the nail, even though we're not interested in the wall. It would be the earth acting on the hammer and the nail, even though we're not interested in what the earth is doing. It's all the stuff outside our little system that we've defined. Okay, so external is the key word there. Now we can actually, if we were to draw out all these forces, the interaction diagram essentially just encloses the objects only in the system. Okay, it helps us remember what we're focusing on. And then anything interacting with those objects outside the system, those are just external forces. Okay, so this is interactions, objects with their environments. So if we think back to single particle dynamics, we have one object and all the forces acting on it are summed up. So here we have three forces that are summed up. Now we have interacting objects. So Newton's third law, we're not just looking at what one particle does, we're looking at two. Okay, so in this situation, maybe we have two satellites orbiting Earth that are tethered together. Okay, so if that's the case, and we do have these two satellites, this could be Sat1, this could be the second satellite. Okay, and this is Earth. Okay, so the idea here is essentially each line represents an interaction. So we have gravitational interactions. Those are the most obvious. So one satellite has a gravity between Earth and it. Satellite 2, there's a gravity there holding that thing in place. There's also gravity between the two satellites. They both have mass, which means they're both attracted to each other. So there's also a gravitational pull between the two. And, you know, perhaps they're tethered. So there's another interaction. So that's what these lines are for. Each one represents an interaction. It's important to note that some pairs of objects may and can have more than one interaction. But each line only represents one interaction. Okay, you can't double them up. Now that we have our objects identified and all of the things that are causing interactions, we can actually define our system. Okay, so here our system is defined as just the satellites. That's what we're interested in. We know the Earth is there, but it doesn't matter. We don't want to know what the Earth is doing. We want to know what these satellites are doing. All right, so now we have two internal forces as shown here. So that'd be like the tether and gravity between these two objects. But then we have external forces, and that would be the gravity between the satellites and the Earth. Now we can actually apply this in a very systematic way to pretty much any problem we look at. First, we just want to represent each object as a circle with an appropriate label, like we've done. We want to identify the interactions by drawing lines between the circles. Okay, it's important to remember we only want to include one line per interaction. Okay. Now, next, we want to identify the system by enclosing the objects of interest in a box. And this is specific to just the objects of interest. Okay. Finally, we want to take these diagrams that we made and convert them into free body diagrams. So each object gets its own free body diagram, and you'll want to include only the forces acting on each object, not by each object. Okay, and that'll be more clear in just a second. So let's take a look at this example. This is going to include a lot of stuff. Okay, so a 40-kilogram boy works at his dad's hardware store. One of the boy's jobs is to unload the delivery truck. He places each package on a 30-degree ramp and shoves it up the ramp into the storeroom. He needs to shove the package with an acceleration of at least 1 meters per second squared in order for the package to make it to the top of the ramp. One day the ground is wet with rain and he's wearing slick leather-soled shoes. The coefficient of static friction, okay, so he's not moving. The coefficient of static friction between his shoes and the ground is only 0.25. Okay, and the largest package of the day is a 15-kilogram package, and its coefficient of kinetic friction, because it's sliding up the ramp, its coefficient of kinetic friction is 0.4. So the question is, can he give the package a big enough shove to reach the top of the ramp without his feet slipping? Okay, so we have this dense paragraph of information and context. But really the thing we're after is right here. Okay, so there is a lot of information given in this setup, but sometimes it is easier to skip to the end and identify the unknown, the thing we're trying to look for. Once we find that, we can go back and get the information from the problem. Okay, so let's simplify the question. Can he push the package without his feet slipping? Now let's see, we want him to sit still, right? We don't want any slipping, that would be kinetic friction. We want to know what static friction is required to hold him in place, okay? It may be a number so high that his shoes can't do it. We don't know yet. We just need to see what is required. Okay, so we've read the problem. We need to visualize and identify our knowns and unknowns. So here's our picture. Let's see, here's our picture. We know a lot. We're given a lot in this problem. We're given the masses of both objects, the boy and the package. We're given the angle of the incline, the acceleration that's required for this to be successful, and we're given two different coefficients of friction. Remember, the static friction we're applying to the boy because we want him to sit still while he pushes his box. We don't want him to slip. The kinetic friction applies to the box, but we do want that to slip up the ramp and into the storeroom. Okay? Now let's jump over here to this interaction diagram. So we have these two objects, the boy and the package, and it's interacting with all sorts of stuff. Okay? So let's label the interactions between the boy and the package first. Well, the only thing that's happening there is there's just a push, right? The boy is pushing on the package. The package is pushing back because of Newton's third law. Okay, well, that was easy. Well, that's really the only internal force we have between these two objects. It's just the one. Now let's look at the external forces. So we do have friction between the boy and the surface. This is going to be the static friction holding him in place. We also have static friction we have kinetic friction between the package and the surface, because the kinetic friction is going to resist it sliding up the ramp. On that same surface, we have the normal force pushing up on the boy, keeping him from like falling to the earth. And of course, the package, since it's sitting on the ramp, will have a normal force. And then we also have, obviously, the entire Earth is acting on the surface, so there's gravity. But the boy is also being held on the earth by gravity, and the package is being held onto the ramp by gravity. Okay, so we've got 4 different colors in our system. We have 4 different colors, okay, which means we have 4 different forces to deal with. So here's what I'm going to do. I'm going to identify and isolate the boy. You'll notice I have a black, blue, orange, and green line that's leaving my circle. Okay, so that means there's 4 forces that need to be included in my free body diagram. So over here on my free body diagram of the boy, I include those 4 forces. I've got the normal force, I've got gravity pointed down, okay, I've got the force due to friction, static friction, and then I've got that, remember, I don't include the force of the boy pushing, I include only things acting on him. So I include the force of the box pushing back on the boy. Okay, so there's my 4 forces acting on the boy. Same thing over here for the package. You'll notice if I look back at my interaction diagram, I've got 4 different colored lines leaving my my circle here that I've made from the package. That means I have 4 vectors, okay? So I've got my normal force and gravity. Those are obvious ones. Then I also have my kinetic friction that's going to oppose this thing shooting up the ramp. But then I have not the force from the package. I have the force included from the boy. Okay, now here's something that you need to take into account. These 2 things are equal and opposite, okay? Equal and opposite. And that's because of Newton's 3rd law, okay? So we can actually use these 2 vectors to relate both free body diagrams. This is our link between the 2. I'm going to try and write that here. Link between. Ooh, that looks like crap. My apologies. Just know that it says link between. All right. Well, let's start actually setting up the algebra from these 2 free body diagrams. Now I'm going to cheat a little bit. Using Newton's 3rd law, I know that those 2 forces that I just labeled as the link between the free body diagrams, I'm just going to call that force F because it's equal and opposite. So why use this like P on B and B on P if they're the same? Let's just call it F. So for the boy, okay, we're going to sum up all the forces. So we have the force of static friction. We have the force from the box pushing on him. Okay, we have his normal force up from the ground. And we have gravity pulling him down into the ground, counteracting the normal force. We don't want him to move anywhere, so all of this has to add up and equal 0. That's why I have the 0 vector here. All right, now, we know what forces are acting on this boy. We added them up. We know he's in equilibrium, so they equal 0. Right, so let's look at the x direction. Really, in the x direction, the only thing we have going on is just static friction from his shoes, and we also have the force from the package. Okay, so let's not forget that. So I want to label these real quick. Okay, we have static friction pointing to the right. Now remember, this is because the box is trying to push him backwards. The box is trying to push him away from the ramp. So friction is going to keep him from moving away from the ramp. Okay, so we have that piece. We also have a piece of that force from the box, right? That's an adjacent piece to the angle theta, so we'll use cosine. So my orange vectors here, those 2 things are got to cancel each other out to keep this boy in position. We have the full force of friction, but then we have one piece of that force from the box. These, when we add them together, have to equal 0 newtons. Okay, well, this equation gives us something simple. We just move F cosine theta over, and look at what we have. So it turns out this is what we needed for the problem in the first place. We wanted to know what the force of friction is, okay? If we knew what F of S was, we can compare it to see if it's going to be enough to hold them in place. But the problem is we don't know what big F is. We don't know the force of that push. We don't know the interaction between the box and the buoy. Because we don't know that, even though we have an equation for our friction, our static friction, we can't calculate it yet. We can write it out as F cosine theta. So now we need to fill in those blanks. We don't know what F is. We need to figure it out. So for now, let's go ahead and just look at the y direction and see what's going on here. So the y direction for the buoy is a little more difficult. We have his normal force up, we have his weight down, but then we also have a piece of that box pushing him down, right? So let's draw this out. Okay, so for the buoy, we have the normal force up, we have his weight down, but then we also have, and you can see it here on the free body diagram, we also have a piece of this force vector from the box. So that's opposite of the angle, so we want to use sine. All these three vectors, these three green vectors added up, they have to equal 0 as well, because we know we don't want the buoy to move up and down. Okay, now, when I solve for the normal force, because that's a good thing to know, look at what we have. Normally, when we talk about the normal force, we say, oh, our weight's down, the normal force is up, opposing it. But look at what we have here. This normal force, it's his weight plus more. So his normal force is actually more than just the weight of the buoy himself. That's totally fine. It can happen. So what's going on is the normal force has to counteract his weight down and some of that weight of that box. Okay, so the normal force here is doing double duty essentially. So it's okay that, and you'll see it from time to time, the normal force doesn't always just equal and cancel out the weight. It could cancel out multiple things, and that's the case here. All right, let's look at the package. We've done about everything we can with the boys' equations. So let's think about what we can glean from the package. Notice we're still not there yet, because remember, we are trying to figure out what F of S is. We don't know what friction's available. This is what we're trying to do. Right now, we're a little lost because we need to figure out what big F is, that interaction force. So let's look at the equations for the package over here. In the x direction, we have, and this is a different free body diagram now. So in the x direction, we have the force going up. Okay, I can label that in green. Force going up on the package from the buoy. We also have kinetic friction, because that's going to oppose the motion of this box. Okay, that's also just head on the x-axis. We've slanted our coordinate system. We can totally do that. So there's our two pieces already. Now the other thing is we have another piece in the x direction. It's just from gravity, right? So gravity's doing double duty. It's acting in the x direction a bit and the y direction. All right, so here we see that this piece of gravity in the x direction is opposite the angle we're given. So since it's opposite, we're going to use sine, okay? Now we need to stop and think about something. These forces in the x direction, these don't equal 0. This box has to move up. It's going up the ramp, okay? So here's Newton's second law. Every time when all, like over here, when these equal 0, Newton's first law. This one, all the forces added up are unbalanced, so there's an acceleration. F equals ma, okay? So we know this thing's going to accelerate on our y-axis. So that has to equal ma. Well, we can actually start getting closer to this big mystery F. Because remember, if we can figure out F, we can figure out that static friction that we're after. Okay, so all I did up here, I solved for F, but we run into another problem. What's the normal force of the package? Okay, we're so close to figuring out big F, but we're still missing a piece. Well, let's see. We want the normal force of the package, and the normal force usually deals with stuff in the y direction, the up-down direction. So let's look at the components here in the y direction of the box, of the package. Well, we know it's not flying off the ramp or sinking down into the ramp. So this is going to be another Newton's first law where these forces equal 0. Now there's only two pieces. There's the normal force, as I'm showing here on the free body diagram. Okay, so we've got the normal force, but then we also have some of gravity, right? Some of this gravity is holding this box down on the ramp. So we know that this adjacent piece to the angle for gravity, okay, that means cosine, this other component of gravity is holding us down on the ramp. So that's why we're going to use cosine here. Now the difference between these two to keep the thing on the ramp has to be 0. All right, and that's going to give us this nice little relationship here. So we know we've got the normal force of the buoy, which is separate, and the normal force of the package, okay? Now, we can actually use the normal force of the package here to solve for F, which we can then use to solve for F of S. It's getting confusing, but that's okay. This is a very difficult problem to keep up with everything. All right, so let's put all these pieces that are floating around together. From the package's equations, okay, we found the normal force for the package. Okay, we're going to put that into the equation to calculate mystery F. All of this is around the package right now. Okay, yes, that's a gross line, but I literally just plugged in the numbers and the units. Okay, so all I did was once I plugged this in, once this got plugged in, I realized every term had a mass term for the package. So I pulled it out front. Everything else is just an acceleration. So you'll notice I got kilograms out front. Then I have A, which is the acceleration that is required of the package. I have acceleration due to gravity with some terms here. This is just scaling gravity, right? I'm 40% of gravity times this scaling over here of cosine of 30 degrees. These terms over here are just tweaking my gravity to make it fit into the problem. Same thing here. I've got gravity from my third term, g sine theta, and then I just need to scale this piece of gravity too. So all the units here, this is all just acceleration, meters per second squared. So now I have kilograms times acceleration. Well, by George, that is newtons. So this equation works out. And it turns out, since we have values for everything, we know that this mystery force is 139 newtons. Okay, now we can go back to the Boy's equations to determine the required static friction. Okay, well, this is easy. We know what the mystery F is now. We can plug it in. We know what the angle is of the ramp, because the ramp is the key angle here. Now, it turns out that the required amount of static friction is 120 newtons. This is required. Now the question is, can his shoes do that? Okay, this is what's required, but what is possible? Okay, we may not be able to get 120 newtons. All right, so here's what we can do. We can go back to the Boy's equations and actually calculate the maximum friction possible. Okay, so we can't get any more than this. Well, this requires us to know the Boy's normal force, and we do, because we calculated that. That's from his y direction. So all we're going to do is just plug it in. Okay, we now know everything we need. The rest is just plug and chug. There's only 115 newtons possible. That's the maximum amount his shoes can give him. So to answer the question, since the required static friction of 120 newtons is larger than F max, which is only 115 newtons, the Boy cannot push the packages, or at least the one big package, cannot push the package up the ramp without slipping. Well, that's a little disappointing. All right, so let's sum up Newton's third law here. So every force occurs as one member of an action-reaction pair of forces. We've talked about it. We've seen that with this box and this boy. Two members of an action-reaction pair act on two different objects. So the boy acts on the box acts on the boy. The two members of an action-reaction pair are equal in magnitude and opposite in direction. That's important. That's how we linked the two free body diagrams, okay? So this links to free body diagrams. And that's useful. Okay, so this actually completes our definition of force. It's an interaction between objects. Now, something else to note, with these interactions of equal opposite forces, the two objects could have different masses. Okay, so the lighter mass will have a larger acceleration, right? Because there's not much of it, it's going to move a lot, even though the forces are equal. So now if we revisit the ball in free fall that we talked about earlier, in the case where a ball is falling, the ball is going to fall at g, negative g, since we're neglecting air resistance. It is pulling up on the Earth, but because the Earth is huge, super large mass, its acceleration is going to be very small. Like you won't even notice that it's being accelerated up, even though it is by the ball, because the mass differences are ridiculous. You just can't really even detect it. It's so small, but you could calculate it if you wanted to. Another example of propulsion and friction being used is actually getting you around and getting you moving. So essentially, propulsion is when a system uses an internal source of energy to drive itself forward. So when you walk, you actually push the earth away when you step forward. So the whole idea here is that you're applying and using and fighting against static friction. Every time you put your foot down and push forward, you don't want your foot to slip. So the fact that your foot doesn't slip allows you to push yourself forward. Okay, another example is kind of like car tires. They work the same way as feet and shoes do. Put it down, you sort of push the earth away under you, the earth pushes back with that friction, and that's what's going to push you forward. Rockets actually use thrust, or they get their thrust from the gas molecules that make up their exhaust. So the whole idea here is essentially the gases come out, they kind of all get stacked up against each other, and then it sort of gives you something to push off of. That's the way I like to think about thrust. But all of these are sort of examples of friction and interacting objects, either gas molecules or your foot with the ground or a wheel with the ground. You always have two things interacting here. Okay, now we need to just quickly talk about ropes and pulleys, and then we can call it. So in single particle dynamics, tension was defined as the force exerted on an object by a rope or string. Okay, cool. We didn't really care anything about the rope or string. But the tension force is supplied in these ropes or strings essentially by all those little molecular bonds and those springs. We've been thinking about them as springs. So these springs do pull in both directions. Okay, we can see that over here. With this safe hanging from a rope. So this rope has all these molecular bonds in it. That's what makes up the rope. And these little bonds act like springs. So you essentially get these layers of bonds pulling upwards and bonds pulling downwards. So that's why you get tension, which is constant throughout a rope in equilibrium. So essentially everything cancels out. However, there's a case where maybe the string is accelerating, okay? Now the question is, if we have two blocks like this on a string and one starts accelerating, does the tension stay the same through the rope? Because if they're in equilibrium just sitting, yes, the tension's the same. So let's think about this for just a minute. So in this case, the string must have a net force applied to it because it is accelerating, right? So the string must have a net force. So let's break this down and just think about the string in between these two blocks. Okay. So the sum of the net forces on the string, okay, is going to be the tension from B on the string, block B, and then in the opposite direction, okay, so we have one tension going one way, one tension the other. Okay, the opposite is going to be the tension from block A on the string. Now this object or the string is moving, so we know the forces are unbalanced. They have to be unbalanced. So this is going to equal MA. Now look at what we can do. We can say, okay, well, the tension on the B side from block B is the tension on A plus extra, okay? But then the tension on the A side is tension from B minus extra, okay? So one side has a plus MA, the other side has a minus MA. So you can see just from this simple reworking of equations that the tension at the front of the accelerating string is higher, right, plus MA, than the tension at the back where the A block is. Okay, so the tension is actually higher on one side than the other. However, we're going to get around that for this course. If we assume that the mass is really small, like just a tiny little like fishing wire or something, in that case, we can just ignore the mass. So these little MA terms go away. And then we have this statement here. The tensions are essentially equal if the rope or string is small. Okay, now what that means is this is going to transfer forces. Block A and block B are going to be an action-interaction pair, okay? Even though they're not touching, this string or rope, this massless string is going to sort of act like a conduit to let these contact forces actually work as contact forces and not long-range forces. All right, so with pulleys, strings and ropes are often passed over pulleys, obviously. So let's use some simplifying assumptions here. So the string and the pulley are both massless. That'll make things easy. And there's no friction when the pulley turns on its axle, okay? So we're ignoring all these little things that might actually interfere with our forces because we're making simplifying assumptions, okay? So you can see here we've got block A, block B with block B dangling. We also have several forces acting on block A. Obviously, we have the weight of the block, the normal force. But then we have this tension, and you'll notice what happens here with this tension. So we have this tension, it's going in the positive X direction, but then it gets turned to the negative Y direction. So we're going plus X, then all of a sudden we're negative Y. And that's what pulleys do, okay? The tension force gets turned by the pulley. So what starts off in like the positive X direction could wind up being negative Y. Now, we've got this thing transferring these interactions. That's all it's doing. And you can see in our free body diagram of this situation with block A and block B over the pulley. They're linked. Both separate free body diagrams are linked by this equal opposite Newton's third law idea right here, with the tension from one equaling the tension on the other. All right, one more example. So bank robbers have pushed a 1,000 kilogram safe to a second story floor to ceiling window. Okay, they plan to break the window, then lower the safe 3 meters to their truck. Not being too clever, they stack up 500 kilograms of furniture, tie a rope between the safe and the furniture, and place the rope over the pulley. They then push the safe out the window. So what's the safe speed when it hits the truck? Okay, the coefficient of kinetic friction between the furniture and the floor is 0.5, or 50% the normal force. So here's our setup. We have the furniture up top. We have the safe dangling over the truck. What's going to happen here is essentially we're going to identify all the things interacting. So we have a rope, we have the furniture, we have the safe, we have the surface, and we also have the entire Earth. All right, so this is all drawn out. We have our knowns and unknowns, not really given a whole lot. But essentially, we just want to find that final velocity when this thing hits the truck. Okay, and I'll try to make this quick. So let's circle this one, our furniture. So the furniture's got 4 lines. That means there's 4 forces. We can find them here. In the y direction, we have the obvious. This is easy. In this case, the normal force does equal gravity because there's no slant. Okay, so those two are canceling out, and the furniture is just going to slide on the x-axis. All right, which means we have these two in the x direction. Now remember, because Newton's third law and this rope, okay, these two vectors are going to be equal and opposite. Okay, so the pulley is going to redirect this. Instead of positive x, they're going to be negative y now, or positive y, depending on how you set things up. Okay, and then the only other thing here is essentially in the y direction, because we're just dropping something. There's no side by side unless there's wind or something. Okay, so we only have these two, as you can see here. We only have these 2 lines for our safe. Okay, so the furniture, we've got all of these forces added up. Okay, now in the x direction, we can write this out as essentially just the difference between the tension and the kinetic friction equals this unbalanced acceleration. Okay, so we want the furniture to move. We know it's going to move. So that's where this F equals ma comes from. Now we don't know what the normal force is, but typically normal forces are determined in the y direction. This one is easy because there's no weird ramp or anything. Okay, so we have just the normal force equals mg. Now, as far as the safe, we have 2, just those 2 forces acting on it. Okay, so in the y direction, we have essentially tension up from the rope and then the weight down. This is also accelerating, right? As the safe falls, the furniture moves. So this is going to be another F equals ma Newton's second law. Okay, so let's take these, everything I've got boxed here, and let's put them together, okay? So the tension and acceleration in the furniture's x direction is the same as the tension and acceleration in the safe's y direction, okay? So tensions and accelerations are the same for both. These can be set to be equal. But remember, the positive acceleration of the furniture becomes the negative acceleration of the safe because it's dropping, right? So with the furniture, we can make that change right here. This is what we started with, but we can say, oh, hey, this has to equal negative. We want to know the acceleration and velocity of the safe, but that's got to be negative of what the furniture is doing. Okay, so we can slip in this negative. It's totally justified, right? Now, let's see. We can rewrite this a bit and just say, well, the tension is just equal to the kinetic friction that's holding us back minus the Newton's second law part, the ma part. Okay, we're just rearranging that equation. Okay, and this is just from the furniture. Now, from the safe aspect, we can solve for tension here. And this is just the ma part of Newton's second law plus the weight of the safe going down. You'll remember this from the previous slide. Okay, now we have 2 tensions. We don't care what the tension is. We just know it's the same. So we can set these 2 things equal to each other. Okay, we can, just like I did here. So this is, let's see, from the furniture. This one's from the safe. Now, all we need to do is just figure out what A is, because A is going to be the acceleration of the safe. So I'm going to do a little bit of algebra here. And all I'm doing is just getting my A's on one side, G's on the other, and then I can pull those out. So I have A's pulled out, G pulled out. All right, now from here, I'm just going to divide and solve for A. Okay, once I do that, I have all my values I can plug in. Okay, so again, it's always good to keep these things and do everything symbolically first. If you start plugging in numbers, you lose your equations. But this is an equation that you can save for later if you wanted to. Save for later. Yeah, once you derive something, you can use it if the situation arises again. Okay, so from here, I've done all the algebra. I've set my tensions equal to each other. I just have to plug in numbers. And it turns out my acceleration at the safe is negative 4.9 meters per second squared. We want to know what velocity this thing hits the truck at. So we need to go back to our kinematic equations. Okay, need to go back and just grab this one. We don't know, we don't care about time. Okay, the initial velocity is 0. So really we're just left with the simplified version, which we've used before. It's just the 2a delta y. We can quickly plug in our values of different a, of course, instead of gravity. And it turns out this thing, this safe hits the truck at 5.4 meters per second. So I know I went through this fast because I didn't want to make the video super long. I would go back and just watch the algebra happen here. Essentially all we're doing is just summing the forces from both free body diagrams, finding out what is equal, and then setting them equal to each other. Okay, once you do that, you've linked all the information from one free body diagram to the other, and then you can solve for your unknown. And if you have any questions, please let me know.